From this video, I want to talk about a new topic, brute force method. Part C.2, Introduction to Brute Force Method. We used this method once before, so later I will talk about that. All right, so let's start. First, I'd like to give you a description of brute force method. What are the properties of the brute force method? From its name, actually you can guess a little bit. Here, let me just give you some simple properties. First, it is a straightforward approach. So you do not need to apply any special technique. The reason we call it brute force, so many people just do it in a hard way, direct way. So you do not use any technique, any trick, any special way. You do it in a straightforward way. Okay? Yeah. Second, you can always apply it to a problem. Yeah. Given a computing problem, you can always try to use this method first. Actually, the people always try the brute force method at the beginning. Next, in general, it is not the best algorithm. Because you can think about, you do not use any special technique. For a problem that is relatively simple, then the brute force method could give you the best solution. It is possible, could give you best solution, but usually for a relatively hard problem, most of the time you cannot expect to use the brute force method to give you the best solution. Otherwise, we won't call it a hard problem, right? If the brute force method can give you the best solution, we will call it simple problem, right? So you can imagine that. All right, so that's the reason. So we do not expect, so usually we do not expect to get the best solution from the brute force method. Does that mean it has no value? It is useless? It's not. It has its own value. It is still useful. Why? See the next one. It is usually used as the starting point for more advanced algorithms. The reason it is useful is we use it as our starting point. That is useful. So you can think about when you are given some relatively hard problem. Usually you have no idea to get started, right? Because the problem is so hard. Many people, they do not have any idea how to solve it. So in that situation, in your first try, you just try to solve it in any way you can use. Okay? Even it's a bad way, you just want to solve it to get the right answer first. So in your first try, you do not require it's a best algorithm. So in that situation, many people try the brute force way first. So we call it, that's our starting point. So that's the reason it is still useful. All right, so next, the efficiency difference. Because we're not satisfied. So even you solve a problem by the brute force method, most of the time we're not very satisfied with the solution. So we want to improve it. We want to find a much better solution. Here, this one just tells you the efficiency difference between the brute force method and more advanced algorithms could be huge. Could be really, really huge. We have example to see that. Remember, so that's the reason I want to mention this example we just did in, our module 1. Yeah. So this one, polynomial evaluation problem. In that one, we use 2 methods. The first one, brute force method. Second one, Horner's rule. And we compare the difference, right? How big is the difference? I use a simple example, right? 5.8 days versus 1 second. Is that huge? 500, so how much different? 500 million? 500 million, yeah. Is that 500 million versus 1? Yeah, yes, in that category, right? In that category. So you can see the difference is huge. Yeah. All right. Okay. All right. So after our initial discussion, so let us get into the details, learning this method through some example. Yeah. Let me use our old problem. Problem number 4, sort an array. So I put this revisited. So this is not the first time we try to solve this problem. And for this class, we will solve this problem many, many times. About 5 or 6 times. So this is our second time. So the same problem, sorting. Yeah. All right. This time we will use another solution, different solution. So every time we work on the same problem, we try to use a different solution. So you may wonder why, right? So many students, you may ask me this question: why we keep solving the same problem many, many different times, right? It looks silly, right? Why we solve the same problem many different times? Yeah. Here, let me give you the justification, the argument to convince you there is a good reason to do that. Yeah. So let me explain that reason here first. Yeah. All right. Our view on this question is like this. All right. A problem is a carrier, all right? Yeah. Carrier of a set of thinking methods that result in different solutions. So what's that? Yeah. So when we solve computing problems, we need to use thinking, right? We need to use logical reasoning, thinking in our mind. And how well can you do the thinking? That's very important, right? When you do the thinking, do you need to use some special methods? Definitely. Most of the time, if you want to solve those computing problems efficiently, you need to use some very smart methods. All right, so here the question is, how do you get those different thinking methods? How do you get those different thinking methods, right? So based on your learning, right? Based on your learning, all right. But here, how to carry those thinking methods, right? Carrier. So here I use this word, carrier. Aircraft carrier. So here I call it thinking method carrier. So not aircraft carrier, thinking method carrier. Now, why I use this analogy here? Now, because usually when we describe some thinking methods, it is not very easy. We need to use a lot of sentences to describe it. Right? So it is very hard to carry different thinking methods with us in our mind to solve many different computing problems. All right, so now there is one special way to carry it. Make a special computing problem. Here, the sorting problem. All right. Now, this sorting problem can carry 5 or 6 different thinking methods. How about that? 5 or 6 different. So here I just say small number. Yeah. In this class, we will do 5 or 6 sorting methods. So it carries 5 or 6 different thinking methods inside this particular problem. All right. After you learn it, you use this one problem, you can store those 5 or 6 different thinking methods. Then, when you work on other different computing problems, can you borrow 1 or 2 some thinking methods from this carrier, right? Yes, that's the point. That's the value. That's the reason we solve the same computing problem many, many times. All right. Now, the thinking methods are important to help you solve other problems. Definitely, your experience. Now, all these methods will become your experience. You know how to use them. Okay? You do not need to start from scratch. So you can apply these methods directly on many other different computing problems. So that's really nice, right? Yeah. All right, so let's continue. Now, let us use a new way to solve it. The new method, new algorithm is typically rely on a new view on the problem. So we have overview, right? Our overview, selection sort. Think about the selection sort. In that solution, we take a special view, right? The minimum of the current array, that's our view. So we understand this problem using the minimum based view. All right, now we want to use a different method. So you have to change your view. You should not take that minimum view. If you take the same view, you will get the same solution. So here we want to take a different view. All right, so a view is based on a special property. A view is based on a special property. So here we need to develop a special property. Okay, yeah. All right. Let's take observation. What is that property? What is that property? Yeah, so think about that. What is that property? Yeah. All right. Yeah. This step is not that easy. You need to find a good property. Yeah. It's not easy. Yeah. Okay. Now, let's try to find it. Yeah. Based on our analysis, we need to do some analysis to find that property. Yeah. All right. So look at this array. Look at this array. Okay? Yeah. Let's imagine in this way. If an array is not sorted, we assume if an array is not sorted, what special property do we have? Okay? So in the previous solution, selection sort, we assume if an array is sorted, what problem do we have? So we look at it in that way. Here we assume if an array is not sorted, what property do we have? Here. So look at these 2 elements. Yeah. Here, adjacent 2 elements. All right. If it's not sorted, you can find a pair of elements that are out of order. Is that true? Yeah, think about it. You can find two elements in this array that are out of order. Yeah, out of order. So you know the meaning, right? Out of order. Yeah, yeah. Not in the ascending order. Yeah, in a different order. Yeah, out of order here we mean AI plus 1 less than AI. How about that? Less than. The later one, the element at a later position is smaller one at an earlier position. So that's the meaning, out of order. The question is, here, for this important property, so we call it critical property. Okay? Critical property. So we describe this critical property. If the array is not sorted, there must be two adjacent elements that are out of order. Two adjacent elements that are out of order. Try to think about it. Is that true? You can find two adjacent. Yeah. Because if every two adjacent elements are in order, definitely this array must be sorted, right? Think about if every two adjacent elements are in ascending order, this is true everywhere, then the whole array is sorted. That's true. Yeah. So then the opposite, there must be two adjacent elements that are out of order. Out of order. This case. Yeah. So this is the critical property. Okay? Yeah. Yeah, so here I give you the reference for this topic, section 4.1 in our textbook. Yeah. Now, to solve the problem, I want to introduce a concept related to this out of order property. We want to define a special concept. So what's the special concept? Inversion concept. Inversion. Okay, yeah. So what's the inversion concept? A pair of elements A sub I and A sub j. Okay, ij anywhere in the array, indices in the array, not necessarily adjacent. Okay, anywhere in the array, is called an inversion if I less than j and ai greater than aj. So that's the inversion meaning. So you can see this concept corresponds to that out of order phenomenon. The abstraction of that out of order phenomenon. But it is a global out of order, not a local out of order. Global, because these two elements can appear anywhere in the array. Or we say appear globally in the array. Now, for the adjacent case, adjacent inversion, that's the local inversion. We call local inversion. Okay? Yeah. Then no restriction, this case, global inversion. Okay? Yeah. So we try to understand. So there are two type of inversions. One global inversion, another local inversion. Okay? So they are different. So we will compare these two different inversions. Yeah. All right. Yeah. So let's compare here. If the array is not sorted, there must be an inversion. Yeah. So this is our, summarized from that observation. Summarize. Yeah. Although here we have adjacent, but here we do not talk about an adjacent thing. We talk about here the global inversion, right? So here we use the global inversion. Yeah. Yeah. It's okay. It's correct. Okay. It's correct. Yeah. All right. So then, now we want to change to the local inversion way. Yeah, local inversion way. Yeah. If the array is not sorted, there must be an adjacent inversion. Adjacent inversion, that's the local view. Yeah. So we change from the global view to the local view. Yeah. So this is local view. Okay? Yeah. That's the global view. Why? Can you understand why we want to make this change from a global view to a local view? The reason is simple, because it is harder to work on a global view. If you want to work on a global view, you need to do more work, right? You need to look for an inversion globally, everywhere in the array. So that's a lot of work, okay? The more work you do, the slower your algorithm. Yeah. Then let's look at the local view. If you just look for inversion locally to adjacent elements and check them if there is an inversion between them, is that much easier? You do not need to look everywhere. You only restrict to one particular location, right? Yeah. So then moving from left to right, you will do much less work. So that's the point. So that's the intuition we have from this observation. Yeah. Intuition is very important. Yeah. Intuition, yeah, is very important. Yeah. All right, so let's continue. Yeah. All right. The next question is how to fix the problem. Yeah. We agree we have many inversions. The question is how do you fix all those inversions? Yeah. The method is simple. There is one special operation can be used to fix an inversion. Swap operation. Yeah. Can we swap these values of those two elements? We can do the swap operation. Then after the swap operation, that particular inversion is gone. So we reduce that inversion. Only one inversion, okay? Yeah, that inversion. Yeah. We cannot guarantee other places, but that location, we remove one inversion. Yeah. If you can remove one, you can remove all the inversions, right? You just apply the swap operations everywhere when you find an inversion. All right, now we have the implementation idea. Yeah. How to implement? Yeah. Remove all the local inversions by local swap. Yeah. Here you can see our local view is important. Yeah. Because we only work on the local inversions using local swaps. Yeah. Not global inversions using global swaps. So you can see the difference. Yeah. Yeah. All right, the procedure. Yeah. So detail, the procedure. Yeah. We start from the first element for each scan. We scan the array, but we start from the first one to the last one. Okay, yeah. All right. Step number 2, do swaps one by one from left to right. From left to right. Yeah. In order, shifting positions. Yeah. One after another. Yeah. If necessary. Right? So here I put this if necessary because when you check two adjacent elements, there may not be any inversion, right, between them. So then you won't do the swap operation. So if necessary. Sometimes you do, sometimes you do not do it. Yeah. Step 3, stop at the first in place element. Yeah. So here, let me describe the meaning. Yeah. Because here, this phrase a little vague here. All right. When we do the scan, the first time when we do the scan, swap, swap, swap. So you can see after you finish scan the whole array, the last element must be in place, right? Yeah. Because when you do that, swap, 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 you can see the last element must be in place. Okay? Yeah. So try to imagine that. Yeah. Or in other words, the largest element after your scan from beginning to end, the largest element will be swapped to the end. Is that true? Yeah. Because if the largest element in the middle, the largest element will always cause inversion, right? So when you do inversion, the largest element moves to the end, okay, until it reaches the end. So you can see the largest element is always placed at the end of the current array. Okay? It is in place. Now, then your next round of scan, you won't compare with the in-place element, right? You exclude the previous in-place element. So then you put another element in place. Then you exclude it. Another element in place. You exclude it. So every time you stop at the first in-place element, because you keep increasing the in-place elements. Yeah. So there is a block there is whole block at the end containing all the in-place elements. Yeah. But when you hit the first in-place element, so you use some way to store it. Okay? Yeah. You use some way to store it. Yeah, it's very simple. When you hit the first in-place element, you stop. So you go to the next scan. Yeah. That's the step 3. Yeah. So it is, not that clear to explain. So here I just use more words to explain the meaning. Yeah. In-place element. Yeah. All right. So then now our conclusion. Yeah. So you can see we can get the whole array sorted. Yeah. All right. So you can see the solution. Let's look at some basic properties of this solution. So there is one element in place every scan. Yeah, I mentioned that in our discussion. Next, the in-place element of each scan appears at the end of the current array. Yeah. Next, the current array is a subarray that excludes all the in-place elements. Yeah. So that's in our discussion. Yeah. We find all these properties. Yeah. Now, conclusion, or let's do some summary. Yeah. Visual imagination. Yeah. Some of you may feel this method sounds familiar. Yeah. Yeah. Sounds, not that new. Why? Yeah. The swap looks like a bubble moving to the right. Bubble, remember this name bubble, right? Yeah, bubble sort. This is the so-called bubble sort. Yeah. Yeah. Although, because we learned the bubble sort before. Yeah. Why I just repeat the bubble sort another time? Yeah. Originally, I may not like to repeat those bubble sort, but the reason is here we take a different view on it. We want to explain different concepts, inversion concept. And we also want to introduce some new ideas. Thinking methods carrier, right? So many different ideas we want to use this old example to explain. So that's the reason. So we bring it back and, do some more discussion. Yeah. All right. Next, analysis. For the analysis here, I do not repeat it another time because it is very similar to that of the selection sort. You can see, when you look at each scan, just like the same scan in the selection sort. Yeah. The result also the same. The analysis, the result number also the same. Yeah. All right. But here, before we end this video, let me ask you the final question. what is the basic operation in the bubble sort. You may notice there are two operations, and which one is the basic operation? Comparison and swap. Comparison, you need to do comparison, right? How do you know two adjacent elements have an inversion? Right? How do you know? You need to do comparison to know it, right? So comparison in order to get an inversion, right? Yeah. After you detect an inversion, then you do the swap operation. Yeah. Here my question. Which one is the basic operation? Comparison operation or swap operation in this method? Okay, yeah. My answer is comparison is the basic, not swap operation. Can you understand why? Can you understand why? Yeah. Basic. Yeah. The reason is this. First, swap operation, we know it is very important in the bubble sort. Swap operation. Yeah. We rely on swap operation to fix all the inversions. So it's very important. Yeah. Second, swap operation is much slower than a comparison. One swap is much slower than one comparison. So why? So let me use this simple example to explain. Yeah. Think about when we do swap between two variables, A and B, what do we need to do? Yeah. First, we need to get a third variable, C. All right? So then we need to copy value from A to C. Okay? Second, we need to copy value from B to A. Third, we need to copy value from C to B. All right? So here you can see we need to do 3 assignment operations. So these copy, so also just assignment operation. Okay? Assignment operation. Just copy a value from one variable to another variable. Okay? This copy operation actually is already slower than comparison operation. Compare, you do not do copy, you just compare the value, which one larger, smaller. So it will be faster. Copy, you need to move value from one location to another location. So that's why it's slower than just compare, right? Yeah. First, one copy or one assignment operation already slower than one comparison. But you have 3 assignments. So more than 3 times slower. Yeah. So first, swap slower. Yeah. Second, comparison occurs more frequently than swap in bubble sort. Can you notice that? Comparison occurs more frequently than swap. Why? When you check every 2 adjacent elements, you need to do comparison. But for the swap, only if necessary, right? You do not, sometimes you do not do the swap operations. When you do not have any inversion, why you do swap operation? Right? You do not do swap operation. Yeah. So for the best case in the bubble sort, you never do any swap operation because the whole array is sorted. No need to do any swap operation. So swap operation does not occur as frequently as the comparison operation. So that's the reason we use the most frequently occurred operation as the basic operation. So you can see this is a good example to explain how to choose our basic operations. Yeah. All right, so let me finish this video right here.